Welcome back. In this section, I'm going to dive a little deeper into describing the orbitals that we've just sort of generally discussed, and we've talked about sort of the general idea of what they are and how the electrons occupy them and creating these electron configurations. I want to dive a little bit more into sort of the more theoretical underpinning of why these orbitals and sort of why there's reasons behind why we see these sets of orbitals. So these are what are called the quantum numbers, and these are the numbers that describe the orbitals. Now, these numbers come from Schrodinger's equation. So as we mentioned before, in Chapter 8, this is section 8.5, we talk about Schrodinger's equation. And the solutions to Schrodinger's equation are the wave functions. And the wave functions are used to create the 3D probability maps that are the orbitals. Now, part of the solution to these wave functions, part of the numbers that we get out of these solutions, these wave functions, are quantum numbers. And in particular, 3 quantum numbers that describe the wave function, or in other words, they describe each individual orbital. So each individual orbital is described by 3 quantum numbers. And those are, first of all, the principal quantum number. And this is abbreviated by the symbol n. And the possible values are positive integers, right? So 1, 2, 3, 4, etc. So these are, if you want to think about it, sort of akin to the energy levels that we saw in Bohr's model, right? So they describe basically the orbital energy level and the orbital size. So the bigger that is, the higher the energy, the bigger in size the orbital is going to be. We have what's called the angular momentum, or what some books will call the secondary quantum number. This book calls it the angular momentum quantum number, and it's abbreviated by this sort of script L. And it has possible values of integers between 0 and n minus 1. So for example, if you have an n of 1, then the only possible value is 0, right? Because it can be 0 and n minus 1 or 1 minus 1 is 0, so the only possible value is 0. But if n is 2, then you have 0, and n minus 1 would be 2 minus 1 or 1, so you have possible integer values of 0 and 1. If it's 3, you have between 0 and n minus 1, so 3 minus 1 would be 2, so you have the integers between 0 and 2, or 0, 1, and 2, etc. So L can have possible values, all the possible values between 0 and n minus 1. Now, this is where we start to see the patterns. So the integers, or L, represents the shape, what are sometimes called the sublevels or subshells, but I like just to think about it as the orbital shape. So in other words, they describe the type of orbital it is, the S or the P, right? And so if you have L, and I'm just going to draw this down here, and L of 0 equals an S orbital, and L of 1 equals a P orbital, and L of 2 equals a D orbital, and L of 3 equals an F orbital. So if we remember, on the second energy level, we have both S and P orbitals, right? Represented by these 2 L values. On the third energy level, we have S, P, and D. On the fourth, we have S, P, D, and F, etc. And the third quantum number that comes out of Schrodinger's equation is the so-called magnetic quantum number, represented by M sub L. It represents the orientation in space. So how is this orbital shape oriented in 3 dimensions? Now, it has possible values between negative L and positive L. So all the integers between negative L and positive L. So if we look at our table, right, if we have an L of 0, then the only possible M sub value is also 0. So for every time we have a 0, we have M sub L value sets of 0. But if we have an L of 1, then we have possible values of negative L to positive L. So negative 1 to positive 1, and all the integers in that set are negative 1, 0, positive 1. If we have an L of 2, we have everything between negative 2 and positive 2, and so that would be negative 2, negative 1, 0, positive 1, positive 2. Now, notice the pattern again. So in an s orbital, right, which is equal to 0, we have only one possible M sub L value, right? And in an S, we have just one orbital, right? But when we have a p-type orbital represented by 1, notice we have 3 possible M sub L values, or in other words, 3 possible orientations. And notice p orbitals always come in sets of 3. For a d orbital, right, remember, they come in sets of 5. Notice we have 5 possible M sub L values representing 5 possible orientations of this type of orbital. So now, based on these solutions, I'm sure we can see where these sort of, what may seem sort of arbitrary sets of orbitals are coming from. And if we sort of follow along, we can sort of see that, we have either 1, 3, 5, 7 orbitals. Since every orbital can have 2, the number of electrons that can be in these sets is twice the orbitals, right? So all of the p set can always have 6, a d set can always have 10, an f set can always have 14. Now, those are the 3 quantum numbers that come out of Schrodinger's equation. Now, the 4th possible quantum number is a property of the electron itself. So the first thing to think about is that every single orbital has a unique set of quantum numbers, right? So if I have, let's say, a 2s orbital, a 2s orbital is going to have an n of 2, it's going to have an L of 0, and it's going to have an M sub L of 0. So it's going to have a 2, 0, 0 as its quantum numbers. It's those 3 quantum numbers. Now that's going to be different than, say, a 2p orbital. Now, if we get specific, we'll just say it's the 2px orbital, right? Well, it's going to have an n of 2, but it's a p, so it's going to have an L of 1. Now, we don't really get into distinguishing it, but it's going to have one of the possible M sub L values. So let's say the x, right, is the -1. So it's going to have 2, 1, -1. Now the other p orbitals would be 2, 1, 0, and 2, 1, +1. Right? So each of those p orbitals would have a unique address, if you will, right? So this set of 3 quantum numbers is unique to every orbital, and it's sort of its zip code, right? It's the way that this orbital is described. Now the 4th quantum number, the so-called spin quantum number, which is abbreviated M sub s, is a property of the electron. Now remember we said that there's 2 electrons in each orbital, and they have opposite spins. We mentioned that. And so there's 2 possible values for the spin quantum number, +1/2, -1/2. And so of the 2 electrons in an orbital, one will have a positive half spin, the other will have a -1/2 spin. And so what this ensures is going back to what we saw with the Pauli exclusion principle, which basically said no 2 electrons can have the same set of 4 quantum numbers. And that's true. So let's say we're talking about the 2s orbital. right? The 2 electrons that can be in that 2s orbital will be 2, 0, 0, positive 1/2 and 2, 0, 0, negative 1/2. So every single electron will have its own unique set of 4 quantum numbers. So 3 of them describe the orbital. The 4th one differentiates the 2 electrons within that orbital. And so the quantum numbers provide that sort of mathematical reason or explanation of why the orbitals exist in the way that they do, right? These are what comes out of solving the Schrodinger's equations. We get the wave functions. The wave functions are described by these quantum numbers, and every wave function represents a unique orbital with a unique set of quantum numbers. All right, so the next thing that we're going to talk about, and we'll do this in the next set, is we're going to move on and start looking at some of the material at the end of chapter 9, which is some of the periodic properties or some of the properties of the elements that we can get by sort of taking advantage or looking at these electron configurations and coming up with what are some of the properties that we can base off of knowing or understanding these electron configurations, or what we call periodic trends.